Let's move on to part 2, determining the ion concentrations and the pH of an acid ionization. Usually the Ka equation is used to find the H3O plus concentration, and this H3O plus concentration can be used to find the pH of this acid solution. Now, why is that? It's because the concentration of H3O plus is equal to the concentration of H plus that came off the acid. And all of this H plus binds to water to form H3O plus. So essentially the concentration of H3O plus is equal to the concentration of H plus. So we can use the concentration of H3O plus to find the pH of the solution. Now I'm going to show you how to solve for the H3O plus concentration when we're given a certain concentration of an acid. And so let's say basically we have 0.4 molar of acetic acid, HC2H3O2, in solution. So it's dissolved in our solution. The Ka for this acid, its acid dissociation constant, is 1.8 times 10 to the negative fifth. And we need to find the H3O plus concentration first, and then the pH. So to solve this problem, we have to know first what actually happens when acetic acid dissolves. So when this acid dissolves in water, it produces H3O plus, the hydronium ion, and its anion, C2H3O2 minus. And here's this equation for it dissociating. And we know that this extra H right here, this extra H, comes off this acid, and it goes to H2O to produce H3O plus, and leaving this part with only C2H3O2 minus. So that is how the reaction of the acid goes in water. Now remember, when we dissolve an acid, that does not mean that the acid dissociates. Dissolving and dissociating are two different things. So when we dissolve this, only a portion of it actually dissociates. We can dissolve the entire acid, but only a portion of it actually comes apart and forms H3O plus and C2H3O2 minus. That is called dissociating. So based on this reaction, we can draw the equilibrium equation for the acid, which we can then use to find the concentration of the H3O plus. Now we know that we draw the products multiplied, the concentrations of the products multiplied, H3O plus and C2H3O2 minus. And then we draw the concentration of the acid remaining on the bottom, HC2H3O2 on the bottom. This is the concentration of the acid remaining after the equilibrium has passed. So, however, we do not know how much of this actually dissociated. We only know, here it's given, the initial concentration, which is 0.4 molar. And we're also given the Ka value. So we can plug in the Ka value right here. Ka is 1.8 E minus 5. And we can plug in the 0.4 molar as the initial value of this acid, HC2H3O2. And we do not know what concentrations of these products are produced, so we just plug X and X for them. And I'll explain why it's the same X for both of them very soon. So because this 0.4 molar is only the initial concentration, but this concentration right here is at equilibrium once the reaction already proceeded, we have to draw 0.4 molar minus X, indicating that some of this initial concentration of this acid is lost because it dissociates. So it has to be 0.4 minus X. And obviously we replace the Ka here with 1.8 E times 10 to the negative fifth. So why do we draw X and X here? Why is it the same thing for both of these? Well, when an X amount, an X concentration of this acid is lost in this reaction, it reacts when an X amount of this acid reacts. an X amount of H3O plus and an X amount of C2H3O2 minus is produced. Because these are in a 1-to-1 ratio. Here, HC2H3O2 is in a 1-to-1 ratio of H3O plus, and it is in a 1-to-1 ratio of C2H3O2 minus. That means that for every X of this dissociated, an X amount of H3O plus gets produced and an X amount of C2H3O2 minus produced. Hence, when we took an X away from here, an X amount of this 0.4 molar initial concentration of acetic acid, an X amount of C2H3O2 minus is produced and an X amount of H3O plus is produced. An X and an X on this side. But we do not know these X's. We do not know how much actually gets produced. But we do know that the same amount of concentration that gets taken away here is produced on top of here. Hence, we draw an X and an X for both of these reactants, since they're in a 1-to-1 ratio with this acid. And now we can just simply solve this equation to find the X, the amount, the concentration of both of these products. And once we find the concentration of both of these products after the reaction goes to equilibrium, well, then we know the concentration of H3O plus, and that is already part of the problem solved. And that is exactly what I'm going to do here. First, I take this lower portion and multiply it by 1.8 times 10 to the negative fifth, right here. Then I distribute the 1.8 times 10 to the negative fifth within the parentheses. So here I distribute it and multiply by the 0.4 to get 7.2 times 10 to the negative sixth. And I multiply the 1.8 times 10 to the negative fifth by the minus x to get minus 1.8 times 10 to the negative fifth times x. So I distribute it to each one of these terms. And here I multiply these x's on top to get x squared right here. So this is x squared. And now I will actually bring this x squared to the same side where we have most of these numbers. So it's going to be minus x squared because we brought it to the other side. So in effect, we get this equation. It's actually a quadratic equation. It's minus x squared minus 1.8 times 10 to the negative fifth x plus 7.2 times 10 to the negative sixth. And we know that anyone who took algebra here knows how to solve a quadratic equation. And in case you might have forgotten, I'm here to remind you how. Basically, we recognize that the coefficients here can be assigned like a letter. So a equals -1, this is the first coefficient. B equals the second coefficient, which is this one because it has this x to the first power. So it's b equals -1.8 times 10 to the negative fifth. And c is the last coefficient because it has no x's close to it. It is 7.2 times 10 to the negative sixth, and it's positive. And now based on this, we can plug these a, b, and c, the numbers that correspond to them, into our quadratic equation right here, which you might have probably learned in high school, although you might have forgotten by now. And we know that negative b can go right here, times negative here, and a and c, and a on the bottom. And we essentially, from this quadratic formula right here, this equation, we get one x and a second x. And we need to choose which x is correct. Well, actually, when I solved this problem, I got two of these x's. I got a positive one, 0.00267 molar, and I got a negative one, negative 0.00267 molar. Which one is correct? The correct one for any of these concentration problems is always the positive one. You never choose the negative one because it's impossible to have a negative concentration of a substance. The concentrations have to be positive. And also the concentration here produced, let's say both of these x's are positive, then you choose the x that is less than the initial concentration of this acid. Because since the acid dissociates in a 1-to-1 ratio to the product produced, you cannot have more of this concentration produced than the concentration of the acid initially. That would be physically and chemically impossible. So in this case, the concentration 0.00267 molar is significantly lower than 0.4 molar of the initial acetic acid concentration. Now, that would be our concentration of H3O+. However, if let's say you do not want to actually solve this quadratic equation on paper, since I will admit it does take quite a while, and you might not have that time on the exam, I will provide you with a shortcut to solving this quadratic equation. Since most of you are probably using calculators to solve these problems, there are some apps you can use on your calculator to solve these quadratic equations. First, I'll show you how to solve it on your scientific calculator and then on your graphing calculator. So, for our scientific calculator, let's say, I would turn it on, and then I can go and press second right here, second, and then I will go to the blue right here that says poly solve. So you can see it says poly solve on top. It's the cos button. And here we have these quadratic equations we can solve. But we know that this quadratic equation right here is the x squared form. So we click on the first one. And we can just plug in all of these coefficients right here into here to get it automatically. So for the first one we have -1, so -1 entered. Then we have the second one, b, it's -1.8 times 10 to the -5, so -1.8 minus 5. And then for c we get 7.2, -6. And these are all of our coefficients entered here. Now we can just press solve, and boom, we get the x's for this equation. The first x is 0.00267, just like here. And the second one is -0.00267, just like here. Now, on your graphing calculator, there is a similar thing. And it depends on which calculator you use, but I believe most of these graphing calculators have this function built in. If you do not have it, I think there's a way of downloading it online. So you have to go to the apps button right here. And once you go to the apps, you scroll up and you go up to number 9 right here. It says polysimult. It's polynomial simulation 2. And you click it, and then you click it again. And then you go to the first one option right here. You go to poly root finder. And you go to the second order. All of these problems are going to be second order because it's x squared. So you go second order. And you can click this button right here to go to the next. And then you put in all of your coefficients right here. So the first one is -1. The second one is -1.8 times 10 to the -5. And the third one is 7.2 times 10 to the -6th. And now you just click this again and press solve, and again you get the same thing, -0.00267 and +0.00267. They're basically the same, but you have to take the positive answer here. So that is how you do it the short way. If you're pressured for time on the exam, you don't have to solve all of this stuff. You can just show that you're going to solve it via a polynomial and just get these answers. Okay? Now that we know the concentration of H3O+, we can find the pH in this problem. In order to find the pH, we'll use the formula -log of the H3O+ concentration. You can memorize this formula by knowing that the P in pH stands for -log of something, and the H obviously stands for the H+ concentration. When you combine the P and the H, you get pH, and that will be the -log of the H+ concentration. We also know that the H+ concentration from the acid equals the H3O+ concentration in this solution, because all of the H+'s combine with water to form H3O+. Therefore, the pH of the solution equals -log of the concentration of H3O+. So, we just simply plug in this concentration of the H3O+ into the -log formula, so -log of 0.00267 right here, and we get a pH of 2.573. Now for significant figures of the pH, the rule goes that the number of significant figures in the concentration is the same number of decimal places in the pH. So here we have 1, 2, 3 significant figures in our concentration of H3O+. Therefore, we have 1, 2, 3 decimal places in the pH. So the number of significant figures in the concentration equals the number of decimal places in the pH. That is the significant figure rule for these types of problems. Now, believe it or not, there is an even easier way to solve this problem to find the concentration of H3O+. And this way involves an important approximation. And this is a very important method because it's very frequently used on exams where there's a time pressure and you have to solve things quickly. And sometimes you do not have the time to solve the quadratic equation. It's just too difficult. So this approximation will make this problem extremely easy to solve. So again, we have our reaction on the top where HC2H3O2 dissociates to form H3O+ and C2H3O2-. Previously, we determined that the concentration of this H3O+ for this problem is 0.00267 molar. Now, we can solve this problem a different way. But we start out with the same step initially. We draw our equilibrium equation here, with the Ka equaling the two x's on top for each one of these, x times x, and on the bottom the 0.4, the initial concentration of acetic acid, minus x, the concentration of it that dissociate to form the x on top and the other x on top. Now here we do not have to write 0.4 minus x, surprisingly. In fact, we can take away this x to just write 0.4. Now why is that possible? It's because that when we previously saw that the concentration of H3O+ formed is 0.00267 molar. And since x of this concentration formed 0.00267 molar, then the same x of this concentration was taken away. So this minus x is equal to the x on top. So if 0.00267 molar formed on top, 0.00267 molar was formed on the bottom. So if we were to plug in 0.00267 molar for this x on the bottom, we would get 0.4 minus 0.00267 molar. And this will give us 0.397 molar. Notice that the change here is very small. We only change from 0.4 molar to 0.397 molar. It's so close that 0.397 molar can actually be rounded to 0.4 molar. It's just essentially the same. It's essentially no change because this x is so small. It is so ridiculously small relative to this 0.4 because 0.00267 is much smaller than 0.4 molar because so little of this acid dissolved that the concentration of this acid, this 0.4 molar, changed very little, only to 0.397 molar when the equilibrium was established. However, when we need to find the x on top, we can actually take out this x because there was so little of this x that it essentially does not affect the lower part of this equation. And therefore we can get rid of this x and just pretend as if the initial concentration of this acid stayed the same. Because it essentially did. It's just so little of it dissolved, as you can see. So little of it actually dissolved in this reaction that we can approximate here that the x was negligible. And we can take it out here and just keep the 0.4. Otherwise, for precision, we can just put 0.397, but that won't make much of a difference in what we find for x, because 0.397 and 0.4 are virtually the same. So we take out this x on the bottom, using our small number approximation, because we know that this x is so ridiculously small that we don't need it. And now this becomes a lot easier to solve. All we have to do is multiply this 0.4 by the Ka, so 1.8 times 10 to the negative fifth times 0.4. And this equals the x squared. The x is on top. And we get 7.2 times 10 to the negative sixth after that, because 1.8 times 10 to the negative fifth times 0.4 is 7.2 times 10 to the negative sixth equals x squared. Now we square root the 7.2 times 10 to the negative sixth to find the x, and the x would equal 0.00268 molar. It's slightly different from our previous answer of 0.00267 molar, because we took out this x on the bottom. But is it really that different? 0.00268 molar, it's basically the same as 0.00267 molar. It's so similar. So it becomes, and on the exams, they usually accept both answers. So you can either solve it the quadratic way or this easy way where you don't need the x because it's just too darn small on the bottom. So you can just keep this 0.4, take out the x because it doesn't make a difference on the bottom. You can just find the x on the top. And that is why you don't have to solve the quadratic equation. And that is why this is the easy way. And you get the answer 0.00268 molar. And it's very fast, actually. You can do this very fast. Just solve this equation that's much faster than solving a quadratic. But we cannot always use this approximation, unfortunately. We cannot always assume that this x is so small that we can ignore it. We can only use this when the initial concentration of this acid, this 0.4 molar right here, is equal to or greater than 100 times the Ka times this 1.8 times 10 to the negative fifth. So if this initial concentration of the acid is 100 times or more greater than the Ka, then we can use this concentration, because that means that this Ka is so tiny in comparison to the initial concentration that so little of this acid dissolves that we do not actually care about this minus x on the bottom. We can essentially keep the initial concentration of this acid. And in this case, the 0.4 molar is obviously much greater than 100 times 1.8 times 10 to the negative fifth. That means that so little acetic acid dissolves that we can essentially ignore this x and solve this problem. And this is what I call the small number approximation. It is very simple to solve and is much simpler than solving the quadratic equation. And I would recommend using this for any problem where you can use this small number approximation. Very simple to solve.